Imagine a black hole, twice the mass of the Milky Way, glowing fiercely in the cosmic dark, only it's not just any black hole. It's a baby one, less than a billion years old, siphoning gas from a tangled web of newborn galaxies, all cradled in the universe's infancy. The James Webb Space Telescope caught this rare snapshot, a primordial monster, still hungry, growing inside a cluster of star-forming galaxies, 13 billion light-years away. This isn't just a distant object, it's a flashbulb moment, revealing how these cosmic engines fueled the universe's earliest growth. The data defies old theories, suggesting black holes didn't wait to mature, they surged ahead, shaping galaxies as they devoured the cosmos. What's more, the web of galaxies around it isn't random, it's a cradle, a nursery for stars and supermassive seeds. This glimpse into the dawn of time isn't just about a black hole. It's about rewriting the story of how the universe built itself. In the vast, ever-expanding universe, the birth of stars and galaxies is a process that unfolded billions of years ago. For decades, astronomers have studied how these cosmic structures formed, but many mysteries remain. Recently, a groundbreaking observation has shed new light on this ancient era. The James Webb Space Telescope, or JWST, has captured a rare glimpse of a black hole in its infancy, growing within a network of young galaxies. This discovery is significant not just because it reveals a previously unseen phenomenon, but because it challenges our understanding of how supermassive black holes and galaxies evolved together in the early universe. Let me explain what this means and why it matters. Black holes are among the most mysterious objects in the cosmos. They are regions of space where gravity is so intense that not even light can escape. While we know that supermassive black holes, millions or billions of times the mass of our Sun, reside at the centers of most galaxies today, their origins remain a puzzle. How did these massive entities form? And what role did they play in shaping the galaxies we see around us? These questions have driven much of modern astrophysics. Now, the JWST's observations of an early black hole growing within a web of young galaxies are providing critical clues. To understand this discovery, we need to step back and consider the timeline of the universe. The Big Bang occurred around 13.8 billion years ago, and in the first few 100 million years, the universe was a chaotic mix of gas and dark matter. Over time, gravity pulled this material together, forming the first stars, galaxies, and clusters of galaxies. The process was slow, complex, and not fully understood. But one thing is clear: galaxies and their central black holes are deeply connected. As galaxies grow, their black holes grow too, and vice versa. This mutual influence is thought to be a key driver of galaxy evolution. The JWST, launched in 2021, is uniquely suited to studying this early period. Unlike its predecessors, which primarily observed visible light, the JWST is optimized for infrared wavelengths. This allows it to peer through the dust and gas that obscure distant objects, revealing the faint glow of ancient stars and galaxies. Its powerful instruments have already transformed our view of the cosmos, but this recent discovery takes its capabilities to a new level. The observation in question focuses on a region of space where a black hole is actively growing, surrounded by a network of young galaxies. This is not just a single galaxy, it's a complex web of structures, all forming and evolving in the early universe. What makes this finding so remarkable is the rarity of such a phenomenon. Black holes in the early universe are typically found in isolated galaxies, and their growth is usually studied in the context of their host galaxy. However, this observation suggests a different scenario: a black hole growing within a dense network of young galaxies. These networks, often referred to as cosmic webs, are vast structures of gas and dark matter that connect galaxies across the universe. They act as nurseries for star formation, where gas collapses to create new stars and galaxies. The presence of a black hole within such a web is unexpected, yet it offers a unique opportunity to study how black holes and galaxies interact in their earliest stages. The key to understanding this discovery lies in the black hole's activity. Supermassive black holes in the early universe are thought to have grown rapidly by accreting gas and merging with other black holes. However, the exact mechanisms driving this growth are still debated. In this case, the JWST's observations suggest that the black hole is actively feeding on surrounding material, emitting powerful jets of energy and radiation. This process, known as accretion, is what powers the luminous phenomena we observe, such as quasars. The presence of such activity in a network of young galaxies implies that the black hole's growth is not isolated but is somehow linked to the broader environment. But why is this observation considered rare? For one, the early universe was a time of intense activity, with galaxies forming and merging at a rapid pace. However, the conditions necessary for a black hole to grow in such a network are unlikely. The gas and dark matter in these webs are typically spread out, making it difficult for a black hole to gather enough material to sustain rapid growth. Additionally, the light from such a distant object is extremely faint, requiring the JWST's advanced technology to detect it. The fact that this black hole is visible at all suggests that it is either exceptionally active or that the surrounding environment is unusually dense, providing the necessary fuel for its growth. This discovery also raises important questions about the relationship between black holes and their host galaxies. In modern galaxies, the growth of a supermassive black hole is thought to be regulated by the galaxy itself. For example, as a galaxy forms, its gravitational pull influences the black hole's growth, preventing it from becoming too massive. However, this observation suggests that in the early universe, the connection between black holes and their environments may have been more dynamic. The presence of a black hole within a network of young galaxies implies that the surrounding structures may have played a more active role in its growth, rather than simply being a passive backdrop. To put this into perspective, imagine a cosmic nursery where stars and galaxies are being born in a dense, interconnected web. In this environment, the black hole is not just a passive observer but an active participant in the process. Its growth could be fueled by the gas and dark matter surrounding it, creating a feedback loop that influences the formation of nearby galaxies. This scenario challenges the traditional view that black holes and galaxies evolve independently, instead suggesting a more intertwined relationship. Such a dynamic could explain how supermassive black holes reached their massive sizes so quickly in the early universe. The implications of this discovery extend beyond the study of black holes. Understanding how these massive objects formed is crucial for unraveling the broader story of cosmic evolution. The early universe was a time of rapid change, with galaxies forming, merging, and evolving in complex ways. By observing a black hole growing within a network of young galaxies, we gain insight into the conditions that shaped the universe's structure. This could help us better understand how galaxies like our own Milky Way formed and how their central black holes developed over time. Moreover, this observation highlights the importance of the JWST in studying the early universe. Its ability to detect faint, distant objects has already led to numerous breakthroughs, from the discovery of ancient galaxies to the study of star-forming regions. This particular finding demonstrates how the telescope's capabilities are pushing the boundaries of what we can observe. By capturing light from a black hole that formed just a few 100 million years after the Big Bang, the JWST is providing a window into a time when the universe was still young and undergoing dramatic transformations. It's also worth noting that this discovery is part of a growing body of evidence suggesting that the early universe was more complex and dynamic than previously thought. While we have long known that galaxies and black holes are connected, this observation adds a new layer to that understanding. It suggests that the interplay between black holes and their environments may have been more intricate, with feedback mechanisms and interactions playing a key role in shaping the cosmos. This could have far-reaching consequences for our models of galaxy formation and the role of black holes in the universe's evolution. In conclusion, the JWST's observation of a black hole growing within a network of young galaxies is a rare and significant event. It provides a unique glimpse into the early universe, revealing how supermassive black holes and galaxies may have evolved together. This discovery not only challenges existing theories but also opens new avenues for research. By studying such phenomena, we continue to unravel the mysteries of the cosmos, piece by piece. As we look to the future, the JWST and other advanced telescopes will undoubtedly play a crucial role in expanding our understanding of the universe's origins and its ever-changing nature. So, how did scientists manage to catch a glimpse of a black hole in the early universe, growing within a network of young galaxies? It starts with the James Webb Space Telescope, the most powerful observatory ever launched. Launched in 2021, it's positioned 1 million miles from Earth, where it can peer into the cosmos without the interference of Earth's atmosphere. Its instruments, like the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, are designed to detect faint light from distant objects, stretching back billions of years. But even with these tools, the task was immense. The black hole in question, part of a rare cosmic phenomenon, was so far away that its light took over 13 billion years to reach us. That means we're seeing it as it was when the universe was just a few 100 million years old, a time when galaxies were still forming, and black holes were just beginning to grow. The challenge wasn't just the distance, it was the faintness of the signal. Black holes themselves don't emit light, so scientists had to infer their presence through indirect clues, like the way they pull in surrounding material or the gravitational effects they exert on nearby galaxies. The JWST's ability to capture high-resolution images and spectra of such distant objects made this possible, but it required years of planning, data collection, and analysis. The process began with targeted observations. Scientists used the telescope's advanced sensors to scan regions of the sky where early galaxies are thought to form. These regions, known as high-redshift fields, are areas where the light from ancient galaxies is stretched into longer wavelengths due to the expansion of the universe. By focusing on these fields, researchers hope to find signs of massive black holes in the early cosmos. The JWST's instruments, especially its spectroscopic capabilities, allowed them to analyze the light from these distant objects in unprecedented detail. Spectroscopy breaks down light into its component colors, revealing information about an object's temperature, composition, and motion. For black holes, this technique can help identify the presence of accretion disks, hot, glowing rings of gas and dust that swirl around the event horizon. The light from these disks is intense and can be detected even across vast cosmic distances. But detecting a black hole in the early universe isn't just about finding a bright signal. It's about uncovering subtle clues in the data. The black hole's gravitational influence on its surroundings, for example, can distort the light from nearby galaxies, a phenomenon known as gravitational lensing. By studying these distortions, scientists can estimate the mass of the black hole and its relationship to the host galaxy. However, the data from the JWST isn't immediately clear. Raw images and spectra are complex, requiring sophisticated algorithms to process and interpret. The team spent months calibrating the telescope's instruments to ensure accuracy, adjusting for factors like cosmic background noise and instrumental artifacts. They also had to account for the fact that the light from these distant objects is faint and often blended with other sources. This meant sifting through massive datasets, using machine learning and manual analysis to isolate the signals of interest. The breakthrough came when they identified a cluster of young galaxies, each containing a central black hole, forming a network that spanned millions of light-years. These galaxies, still in their infancy, were actively forming stars and hosting black holes that were growing at an extraordinary rate. The JWST's ability to resolve these structures at such a distance was a testament to its technological prowess. But the discovery wasn't just about the telescope's power, it was about the patience and ingenuity of the scientists involved. The process of confirming the black hole's existence required cross-checking data from multiple instruments. For instance, the NIRCam provided high-resolution images, while MIRI captured the infrared light from the accretion disks. By combining these datasets, the team could build a more complete picture of the black hole's environment. They also compared their findings with simulations of early universe conditions, ensuring that the observed phenomena aligned with theoretical models. This step was crucial because it helped rule out alternative explanations, for example, the possibility that the light they were seeing was from a different type of object, like a massive star or a neutron star. The confirmation process took years, as the team refined their models and validated their results against existing data from other telescopes. The James Webb Space Telescope isn't the only tool in the astronomer's arsenal, but its unique capabilities made it indispensable for this discovery. Before JWST, other observatories like the Hubble Space Telescope could detect faint objects, but they lacked the sensitivity and resolution needed to study the earliest galaxies in such detail. The JWST's larger mirror and advanced detectors allowed it to capture light from objects that were previously invisible, providing a clearer view of the universe's infancy. This technological leap was the result of decades of research and development, with engineers and scientists working tirelessly to overcome the challenges of building a space telescope capable of such feats. The discovery itself was a culmination of this effort. The team's observations revealed that the black hole was growing at a rate far exceeding theoretical predictions. This rapid growth suggested that the black hole was feeding on a vast reservoir of gas, possibly from the surrounding galaxies in the network. Such a finding challenges existing models of black hole evolution, prompting scientists to rethink how these cosmic giants form and grow. However, the process of interpreting these results was equally complex. The team had to consider factors like the density of the galaxy network, the availability of gas for the black hole to consume, and the role of dark matter in shaping the environment. These questions led to new hypotheses and simulations, further advancing our understanding of the universe's early history. The journey from observation to confirmation was as much about collaboration as it was about technology. Scientists from around the world contributed to the analysis, sharing data, refining methods, and debating interpretations. This global effort underscored the importance of teamwork in modern astronomy, where no single researcher can tackle the vast complexities of the cosmos alone. The significance of the discovery extends beyond the black hole itself. By studying these early galaxies and their central black holes, scientists gain insights into the formation of the first stars, the structure of the universe, and the role of supermassive black holes in shaping galaxy evolution. The JWST's ability to capture such a rare event highlights the power of modern observational astronomy and the potential for future discoveries. As the telescope continues its mission, it promises to unveil more secrets of the universe, each revelation building on the foundation of previous knowledge. The process of discovering this black hole was a reminder of how science progresses, not through a single breakthrough, but through persistent curiosity, technological innovation, and the collective effort of a global scientific community. JWST captures rare glimpse of early black hole growing inside network of young galaxies. This part of our deep dive into JWST captures rare glimpse of early black hole growing inside network of young galaxies focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, the universe has been a canvas of mystery, its deepest secrets hidden behind the veil of time and distance. But as scientists have peered further into the cosmos, they've uncovered a story of cosmic evolution, one that begins with the birth of the first stars and galaxies, and culminates in the enigmatic presence of black holes. Today, we're exploring a discovery that bridges these ancient epochs: the James Webb Space Telescope's rare glimpse of an early black hole growing within a network of young galaxies. To understand how we arrived at this moment, we must journey back through the decades, tracing the evolution of our understanding of black holes, galaxy formation, and the tools that have allowed us to see the universe as it was billions of years ago. The story begins in the 1960s, when the concept of black holes was still in its infancy. Before the 1960s, Einstein's theory of general relativity had already predicted the existence of singularities, points of infinite density where gravity becomes so strong that not even light can escape. But these ideas were largely theoretical, and the scientific community remained skeptical. It wasn't until the 1960s that researchers like John Wheeler and Robert Oppenheimer began to formalize the concept of black holes as regions of spacetime where gravity's pull is irresistible. Yet, even as these theories took shape, the universe's most profound mysteries remain just out of reach. How did the first galaxies form? What role did black holes play in their evolution? These questions would take decades to answer, but the seeds of discovery were already being sown. The 1970s and 1980s marked a turning point. Astronomers began to notice strange, luminous objects in the distant universe, quasars, whose energy output defied explanation. These objects, powered by supermassive black holes at the centers of young galaxies, emitted light so intense that they outshone entire galaxies. The discovery of quasars provided the first concrete evidence that black holes could exist in the early universe, but it also raised new questions. How could such massive black holes form so quickly? And what role did they play in shaping the galaxies around them? These mysteries hinted at a deeper connection between black holes and galaxy formation, a link that would become a central theme in modern astrophysics. The 1990s brought a revolutionary leap forward with the launch of the Hubble Space Telescope. For the first time, astronomers could observe the universe in visible light with unprecedented clarity, revealing the structure of distant galaxies and the motion of stars within them. Hubble's images of the early universe showed galaxies in their infancy, their shapes irregular and chaotic, hinting at the turbulent processes of star formation. But while Hubble's observations provided invaluable insights, they were limited by their reliance on visible light. The universe's earliest galaxies, formed just a few 100 million years after the Big Bang, were shrouded in dust and gas, making them difficult to see. To peer further back in time, scientists needed a new tool, one that could capture light from the faintest, most distant objects. This led to the development of the James Webb Space Telescope, a mission that would redefine our understanding of the cosmos. The James Webb Space Telescope, launched in 2021, is a marvel of engineering and a testament to decades of scientific ambition. Unlike Hubble, which operates primarily in visible light, JWST is optimized for infrared observations. This allows it to see through the cosmic dust that obscures the earliest galaxies and detect the faint light of objects from over 13 billion years ago. But JWST's capabilities extend beyond just seeing further. It also allows astronomers to study the composition, temperature, and motion of distant celestial objects with greater precision. These features make it an ideal instrument for investigating the early universe, where the first galaxies and black holes were taking shape. Yet, even with JWST's advanced technology, the discovery of an early black hole growing within a network of young galaxies remains a rare and significant event. Why? Because such a phenomenon challenges our existing models of galaxy and black hole evolution, offering a glimpse into a cosmic process that may have been more complex than previously thought. To understand the significance of this discovery, we must first consider the prevailing theories about how black holes and galaxies form. For many years, scientists believed that supermassive black holes formed gradually, growing through the accretion of gas and mergers with other black holes over billions of years. However, observations of quasars in the early universe suggested that some black holes must have formed much more quickly, perhaps even within the first few 100 million years after the Big Bang. This discrepancy led to the development of new theories, such as the idea that primordial black holes, formed in the dense, violent conditions of the early universe, might have served as seeds for the supermassive black holes we see today. These theories, while speculative, laid the groundwork for understanding how black holes could exist in the earliest epochs of the universe. The discovery of an early black hole growing within a network of young galaxies adds a new dimension to this puzzle. Instead of observing a single, isolated black hole, astronomers have now detected a black hole embedded within a web of young galaxies, suggesting a more interconnected process of growth. This challenges the traditional view of black holes as solitary entities and hints at a dynamic relationship between black holes and their host galaxies. Such a network could provide the necessary environment for a black hole to accumulate mass rapidly, feeding on the gas and stars within its vicinity. But how did this network form? And what role did the black hole play in shaping its surroundings? These questions remain at the heart of ongoing research, and JWST's observations are providing crucial clues. The significance of this discovery also lies in its implications for our understanding of galaxy formation. For decades, scientists have debated how galaxies like our own Milky Way evolved from the chaotic, clumpy structures observed in the early universe. Some theories suggest that galaxies formed through the gradual merging of smaller protogalaxies, while others propose a more turbulent, violent process driven by intense star formation and supernova explosions. The presence of a black hole within a network of young galaxies suggests that these processes may have been even more interconnected than previously thought. The black hole could have played a dual role, not only as a massive gravitational anchor but also as a catalyst for star formation, its energy and radiation influencing the surrounding gas and triggering the birth of new stars. This idea, while still under investigation, offers a compelling explanation for how galaxies and their central black holes might have co-evolved in the early universe. Yet, the discovery of this rare event also underscores the challenges of studying the early universe. Despite JWST's advanced capabilities, observing such distant and faint objects requires immense computational power and sophisticated data analysis techniques. The light from these early galaxies has traveled for billions of years to reach us, and even the most powerful telescopes can only capture a fraction of the information available. Moreover, the complexity of the cosmic web where galaxies, dark matter, and gas interact in intricate ways means that interpreting these observations requires a deep understanding of both theoretical models and observational data. This interplay between theory and observation is what makes discoveries like this so exciting, as they push the boundaries of our knowledge and force us to refine our understanding of the cosmos. As we reflect on the journey from the early theories of black holes to the groundbreaking discoveries made possible by JWST, it's clear that our understanding of the universe has evolved in tandem with our technological capabilities. Each new mission, from the Hubble Space Telescope to the James Webb Space Telescope, has expanded our ability to peer into the past and uncover the secrets of the cosmos. The recent observation of an early black hole growing within a network of young galaxies is not just a milestone in astrophysics, it is a testament to the power of curiosity and the relentless pursuit of knowledge. It reminds us that the universe is still full of mysteries waiting to be uncovered, and that every new discovery brings us one step closer to understanding our place in the cosmos. The James Webb Space Telescope's recent observation of an early black hole growing within a network of young galaxies has sparked a wave of scientific curiosity, but it has also raised more questions than answers. This glimpse into the cosmos, captured in the earliest epochs of the universe, offers a rare opportunity to study how black holes and galaxies co-evolved in their formative years. Yet, the data from this observation is not without its mysteries. Scientists are still grappling with fundamental questions about the mechanisms driving black hole growth, the role of galaxy networks in shaping these cosmic structures, and the broader implications for our understanding of the universe's evolution. While the telescope has provided unprecedented clarity, the complexity of these systems means that many aspects remain unresolved, leaving room for debate and further exploration. One of the most pressing questions centers on the relationship between the black hole and its surrounding galaxy network. The observation suggests that the black hole is actively accreting material, drawing in gas and dust to fuel its growth, but the exact processes governing this interaction are still unclear. In typical galaxy formation models, supermassive black holes are thought to influence their host galaxies through feedback mechanisms, such as jets of high-energy particles or radiation that regulate star formation. However, this particular case presents a unique challenge. The black hole appears to be embedded within a web of young galaxies, rather than isolated within a single galaxy. This raises the question of whether the black hole's growth is driven by the collective activity of the entire network or if it is a dominant force shaping the network itself. Some researchers speculate that the black hole's immense gravitational pull could be drawing in gas from neighboring galaxies, creating a feedback loop that accelerates its growth. Others argue that the observed activity might be a temporary phase, with the black hole's growth slowing as the surrounding material becomes depleted. Without more data, it is difficult to determine which scenario is more accurate, leaving the dynamics of this system shrouded in uncertainty. Another unresolved mystery lies in the timeline of this observation. The JWST's ability to peer billions of light-years back in time means that the black hole and its surrounding galaxies are seen as they existed in the early universe, approximately 10 to 13 billion years ago. However, the exact age of the system and the rate at which it has evolved remain poorly constrained. Some scientists suggest that the black hole's rapid growth could be a sign of a highly efficient accretion process, possibly fueled by an abundance of gas in the early universe. Yet, others caution that such rapid growth might be an anomaly, challenging existing models of how black holes form and evolve. The presence of a network of young galaxies around the black hole complicates matters further. These galaxies are still in their formative stages, suggesting that the system is relatively young. But how young? And what role did the black hole play in shaping the galaxy's development? These questions highlight the need for more detailed observations to determine the system's age and the timeline of its evolution. The observation also raises intriguing questions about the role of dark matter in these early cosmic structures. Dark matter, which makes up the majority of the universe's mass, is thought to play a critical role in galaxy formation by providing the gravitational scaffolding that allows galaxies to form. However, the exact nature of dark matter's influence on black holes and their host galaxies remains a topic of debate. Some researchers propose that the black hole's growth could be linked to the distribution of dark matter in the surrounding network, with the gravitational pull of dark matter channeling gas toward the black hole. Others argue that the observed activity might be more directly tied to the visible matter in the galaxies, rather than dark matter itself. Without direct evidence of dark matter's role in this system, these hypotheses remain speculative, underscoring the limitations of current observational techniques. Beyond the immediate questions about the black hole and its environment, this observation has broader implications for our understanding of cosmic evolution. The coexistence of a rapidly growing black hole and a network of young galaxies challenges existing models of how galaxies and their central black holes interact. In many theories, supermassive black holes are thought to grow in tandem with their host galaxies, with the two processes influencing each other in a delicate balance. However, this case suggests a more complex interplay, where the black hole's growth might be decoupled from the typical galaxy formation timeline. This could mean that the relationship between black holes and galaxies is more varied than previously assumed, with different systems following different evolutionary paths. Such findings could force scientists to revise their models of galaxy formation, potentially leading to a more nuanced understanding of how cosmic structures develop over time. The rarity of this observation also adds to the mystery. While the JWST has already revolutionized our ability to study the early universe, the specific conditions required to observe a black hole growing within a network of young galaxies are likely extremely rare. This raises the question of whether such systems are common or exceptional. If this is an isolated case, it could indicate that the conditions necessary for rapid black hole growth are highly specific, possibly tied to the unique distribution of gas and dark matter in the early universe. Alternatively, if similar systems are found in the future, it could suggest that these interactions are more widespread than previously thought. The answer to this question will depend on the discovery of additional similar systems, which could provide critical insights into the prevalence of such phenomena. Finally, the observation highlights the limitations of our current scientific tools and the need for continued exploration. While the JWST has provided unprecedented detail, its ability to resolve the fine-scale interactions between the black hole and its environment is still constrained by technological and observational limits. For example, the telescope's sensitivity to certain wavelengths of light may not fully capture the complex dynamics at play, leaving some aspects of the system's behavior unobservable. Additionally, the vast distances involved mean that the data we receive is a snapshot of a system that evolved over billions of years, making it difficult to reconstruct the full history of its development. These limitations underscore the importance of future missions and technological advancements, which could help refine our understanding of these cosmic phenomena. In the end, the JWST's observation of this rare black hole growing within a network of young galaxies is a testament to the power of modern astronomy to uncover the universe's deepest secrets. Yet, it is also a reminder that even with the most advanced tools, the cosmos still holds many mysteries. The questions raised by this discovery about the mechanisms of black hole growth, the role of galaxy networks, the influence of dark matter, and the broader implications for cosmic evolution will likely drive scientific inquiry for years to come. As researchers continue to analyze the data and refine their models, this observation may one day serve as a cornerstone for a more complete understanding of how the universe formed and evolved. Until then, the interplay between black holes and galaxies remains a fascinating and unresolved chapter in the story of the cosmos. JWST captures rare glimpse of early black hole growing inside network of young galaxies. This part of our deep dive into JWST captures rare glimpse of early black hole growing inside network of young galaxies focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. So, what did we just witness? The James Webb Space Telescope, that marvel of modern engineering, has given us a rare and stunning look into the early universe, a moment in cosmic history when galaxies were still young and black holes were just beginning to grow. This isn't just another image of a distant galaxy, it's a glimpse into a network of young galaxies, where a black hole is actively feeding and expanding. The significance here is immense. For years, scientists have puzzled over how supermassive black holes, those colossal entities at the centers of galaxies, formed so quickly after the Big Bang. These observations suggest that the seeds of such giants might have been nurtured in dense, chaotic environments where galaxies were still in their infancy. Imagine a cosmic nursery, where stars are being born left and right, and in the heart of this bustling region, a black hole is siphoning gas and dust, fueling its growth. This discovery challenges previous models, which assumed black holes grew more slowly, gradually accumulating mass over billions of years. Instead, it hints at a faster, more intense process, possibly driven by the chaotic interactions between galaxies. But why is this network of young galaxies so important? Well, galaxies and black holes are deeply connected. The way galaxies form and evolve is closely tied to the activity of their central black holes. By studying this early phase, we're getting a clearer picture of how these two cosmic phenomena co-evolved. The JWST's ability to peer back in time, thanks to the expansion of the universe, allowed astronomers to capture this moment when the universe was only about 1.5 billion years old. That's just 10% of its current age, but in cosmic terms, it's a baby universe. The black hole in question is already massive, perhaps a few million times the Sun's mass, but it's still in its early stages. This suggests that the mechanisms driving black hole growth might be more complex than we thought. Maybe they're influenced by the surrounding galaxy's dynamics, or perhaps there are hidden reservoirs of gas that feed them rapidly. The implications are huge. If black holes can grow so quickly in these early environments, it could explain how they reached their enormous sizes by the time the universe was just a few billion years old. It also raises new questions. How common were these dense galaxy clusters in the early universe? Were they special, or were they the norm? And what role did dark matter play in shaping these environments? The JWST isn't just capturing images, it's providing data that could rewrite our understanding of galaxy and black hole evolution. But this isn't just about theory. These observations are grounded in real data, collected through the telescope's advanced instruments. The clarity of the images, the ability to detect faint light from such a distant era, all point to the power of this technology. Yet, even with these breakthroughs, there's still so much to uncover. The universe is full of mysteries, and every new observation brings us closer to solving them. So, what does this mean for us? Well, it's a reminder that the cosmos is far more dynamic and interconnected than we once believed. The early universe wasn't a quiet, orderly place, it was a chaotic, vibrant arena where galaxies and black holes were born, collided, and evolved in ways we're only beginning to understand. This discovery isn't just a milestone for astronomy, it's a testament to human curiosity and the relentless pursuit of knowledge. If you found this deep dive fascinating, consider subscribing to FactVerse for daily explorations into the wonders of space and science. And if you have your own theories or questions about how black holes or galaxies formed, we'd love to hear them. Drop a comment below, let's keep the conversation going. Because the universe is full of secrets, and every question we answer opens the door to more. Stay curious, stay informed, and keep looking up.